Hey, so welcome to a quick thing about our next topic. Um, Throughout your time in your math classes, you guys have been using the Cartesian coordinate system. That's the XY plane that was basically named after Rene Descartes, who was a French mathematician back in the late 1500s and early 1600s. Purportedly, it's him describing the position of a fly and trying to come up with a way to describe that. What's actually interesting is as we develop mathematics, quite frequently, various people kind of come up with the same mathematical concepts, sometimes a slightly different notation independently because they're building on knowledge that was already there. And in this case, at least the legend is that Descartes came up with his idea while watching a fly when he was somewhere between 8 years old and 18. We're not sure if that's all that accurate. It's a legend. But as it turns out, you can actually look at the position of something in more than one way. Now, if you think about it, if I wanted to throw a football to somebody and there was a grid there, it wouldn't make sense for me to say throw the football to 4,4. So throw the football to the right 4 units, have it stop, turn 90 degrees, and then go up 4 units. It would make more sense for me to pivot my body, throw directly at that. So I'd have to know the angle that I would pivot and then the distance that I want to throw directly to that. And that actually is a system of finding places in a plane that is called polar. It actually was used by Descartes as well as long as a whole list of other mathematicians. And interestingly enough, although you haven't probably heard of it by this time in your mathematical career, Descartes, who was the one that invented the other one, was already using polar right away, as well as Cavalieri and a whole number of other very, very significant mathematicians. So although we wait kind of till this moment in time for you guys to learn about this concept, it was actually developed almost simultaneously with the idea of the rectangular system is this idea of a polar system. So what we're going to do is take a look at just a little bit of an idea of how polar coordinates work. Now, I will admit that I am going to mess this up a little bit because my brain just thinks about it in a slightly different way. But the way you're supposed to do this is you're always supposed to list a radius first, or in other words, a distance from the origin that you would go, and then an angle that you would move at. So it would be r comma theta. So if we were going to say, look at something like 10 comma pi over 2, and we wanted to label that, then that would say go out a radius of 10. I marked this to make it a little bit easier. And then let's follow that through that 10 to the angle pi over 2. And so this coordinate right here, this polar coordinate, is actually A. And I hope that makes sense. Or if we wanted to go B, we could say something like 7 at pi over 6 would be go out here to the 7th circle and go to the angle pi over 6. Right here, I'll call that guy B. I'm not going to do all the way to M. I'm just going to do a few of these for the sake of this video. We might go a little bit further and say something like 3 at 5 pi over 4. So I would find the angle 5 pi over 4 and go to the 1, 2, 3rd circle right here. I'll call that one C. Now, this is a fairly simple idea of moving our way through, and you can obviously find any value that you want to. But what gets a little bit interesting, though, is we can start creating some real distinct differences in this system. So the first thing that you notice is every single time I picked a positive radius and a positive angle so far. But it actually does not have to be that way. I could say, let's turn to the angle negative pi over 2, which of course is down, and let's go out here to, let's say, the 16th circle. So that would actually be rotate to the 16th circle, which is actually the size of the graph paper that I picked. And let's go to here, and this is going to be D. But you can tell just by the way that I did that someone else could have called that same exact thing 16 at 3 pi over 2. So you'll notice that D and E right here are really the same coordinate. And so that bothers people that we have different representations of the same place, but it's actually okay. There's nothing undefined about that idea. We can go one step a little bit further in the following. Like, imagine that I said the following. What if I said, let's turn to the angle pi, which of course would be over here, but this time let's go backwards 6 units. So point F would be go to the angle pi and go backwards 6 units. So notice that I'm pointing this direction here, but I go backwards because it's a negative radius. And so point F would be over here. And so what you'll see is as we go through this mathematics, you can have positive radii, you can have negative radii, positive angles and negative angles. And in fact, we can be extra obnoxious about that, and we can have negative both. So one more time, imagine this time I said, let's go to negative pi over 4 as an angle, and let's go to the, say, negative 8 as a radius. So this says, let's go down here to negative pi over 4, but then we're going to go backwards, which is going to be along here, and we're going to go out to the 1, 2, 3, 4, 5, 6, 7, 8 circle right there, and this is point G. Now that does get a little bit confusing when we do those things because sometimes it's hard to know if we did well. So one of the things that I thought it might be helpful to do is take a look at a little Desmos window. So I'm going to go ahead and take a look at this little Desmos window. There is a little formula right here that I had to create that allowed me to do that. But you'll notice that I could say for the first point that I did, I had 10 at the angle pi over 2. And you'll notice that it puts a dot at the angle pi over 2, but on the 6th circle. And I could, of course, label that coordinate right there A if I wanted to. And in the same way, I could take a look at maybe one of the last ones that we did where we had maybe it was negative 6 comma pi. Now that's kind of strange. That was the point that we called point F. So of course you could use this as a way to check your answers and see if what you have done makes sense. Now the last one that I did, which was point G, I gave you negative 8 comma negative pi over 4. And so that's sitting right here. And I'll call that point right here. I think we called that G. And you'll notice that this doesn't look like it landed at pi over 4. It looks like it landed at, I guess that would be 3 pi over 4 because that is an opposite angle to negative pi over 4, which is down here. So that does lead to some obvious points of confusion that can happen when people work at it because rectangular coordinates are unique. And that's kind of an important thing is that you have one and only one name for every single point out there. And if I put a dot, everybody would name it the same if they did it right. There's only one answer. But polar coordinates have an infinite number of representations. And that's a little bit strange. Now, that doesn't mean that if I gave you guys 10 comma pi over 2, that there's an infinite number of places to put that point. It means everybody would put that point exactly right. However, if I chose to give you this one right here, there's many, many ways to represent that point. Somebody might call that the angle 5 pi over 4, but somebody else might call the angle negative 3 pi over 4. Somebody else might have gone around the circle more than one time and called it, I guess it would be 13 pi over 4. There's all these different options, which leads me to this thing right here. So what I wanted to do is take a little look at what happens when we try a couple. So I'm going to start very, very easily. Let's just go with some angles that I think would be easy to do. So let's go 8 at pi over 4. Now, I think everybody should understand that that's going to the angle pi over 4 right here in the middle, and it's going out to the 8th radius, sitting right in there. This says, let's go ahead and do the same thing, but let's get there by rotating backwards. Well, I could get there by rotating to the 8th circle, but I could use a coterminal angle by rotating backwards 7 pi over 4. See, again, going here, going 1, 2, 3, 4, 5, 6, 7 pi over 4 would actually be exactly the same value. Somebody else might have said, hey, you know what, I'm going to go to 8, but I'm going to pick the same angle by rotating an extra circle. So again, let's go ahead and add 2 pi to this one. And again, 2 pi would be 8 pi over 4. So that's going to be at 9 pi over 4. And so each of these things should be, they look different, but they should describe the same place that we have right here. Now, last but not least, let's say what happens if I wanted to get there with a positive angle and yet I would like the radius to be negative. So what I could do, which is a little strange, is if I want to have a positive angle, I would need to rotate down to here underneath, which is the angle 5 pi over 4. But let's go backwards 8. Now that is a little strange and that is potentially a little confusing. So let's go ahead and let's check those points out in Desmos and see if I did them okay. So let's go ahead and see how those play out. So my coordinates were 8 at pi over 4. So I've got this point A right here. And then I guess what I'm going to do is I'm going to go ahead and clone all of these so I don't have to keep retyping them. But we had 8 at pi over 4, and then we tried 8 at negative 7 pi over 4. And let's see if that actually landed in the same place, and it did. And then we tried 8 at 9 pi over 4. Let's see if I can put that one in there. It looks like this coordinate right up here is going to get a little crowded. It's got F, G, and A there. And then we last but not least tried negative 8 at 5. Now, so notice if you did negative 8 at pi over 4, it's down here in the wrong place. I'll call that one H. I think H will work. So notice it's in the wrong place, but if I put a negative on that angle to tell the person to go backwards, now all of a sudden, whoops, I should have said 5 pi over 4. I'm not reading my own notes about what I said to do. Let's try 5 pi over 4, and what do you know? They all land in the same place, and they're just different representations of the same value. So I won't do very many of those. Let's just take a look at, say, one more of those. So we'll do a nice, easy guide, let's say 12 at 2 pi over 3. Now that's going to be sitting over here in the second quadrant. Hopefully we're pretty familiar with that by now. And so we could pick the same radius going all the way through. These things say we have to have a distance of 12 no matter what, but this one says go backwards. And so if I wanted one that is below, I'm going to rotate one full circle back, which is 6 pi over 3 to negative 4. Or I could rotate forward 6 pi over 3 to 8 pi over 3. Now keep in mind, all of these are exactly 6 pi over 3 or 2 pi apart. And then the last one is the strange one, because I'm wanting to get to this location right here by rotating forward, but going back. So I'd have to rotate to down here and then go backwards. So this angle in pi over 3s is the angle 5 pi over 3. So rotate down to the fourth quadrant, but go backwards. And again, we have an infinite number of representations of that. And so that is just a quick synopsis of how you plot and understand points in polar. And then in the next video, I'm going to show you how to convert between the rectangular and polar coordinates. Hopefully that's helpful. I'll see you back in class. Bye-bye.